from Bangkok, Thailand. I hope you're all doing fine in your respective places. I'm Jennifer, your MC for today. I would like to thank all of our distinguished speakers, panelists, experts, and of course, all of you for joining us today. Welcome to AIT Tech Talk, a series of events being organized under the AIT Enterprises Alliance to highlight the expertise of AIT in various emerging technologies and developments. This third event on structural engineering, future-proofing the built environment, which is supported by Computers and Structures Inc. USA, will highlight the future trends and innovations in the design and developments of safe and resilient infrastructure that will last and support future generations. We have a full day ahead of us, so without further ado, please allow me to invite AIT Vice President for Knowledge Transfer, Dr. Naveed Anwar, for his welcome remarks.
Good morning, everyone. Jennifer, thank you so much for doing the introduction. And I'm so glad to welcome all the participants and the speakers to this third Tech Talk, as you mentioned, that we are organizing. In fact, this particular event is a continuation of another event that we did a couple of years ago, which was at that time held in person. And we had a very good interaction. We had very good experts coming and joining at that time. In fact, some of the speakers from that event are also, we are honored that they are joining us today as well. So basically, this talk about the importance of future-proofing our built environment and the role of structural engineer is what we're talking about. And I think this profession has been in the backbone of the development of the built environment for centuries. And we just want to highlight that, and we want to bring into focus some of the new developments and the thinking from various experts. And today, really, we are very honored that we have people who are top of their field. They are well known, not only as structural engineers, but also as visionaries. And we will get to hear from them, from many of them. And then later, we will have a chance to actually have discussions with them. And so I think this Tech Talk series, first of all, is about AIT, sharing knowledge with the profession, with the industry, and also inviting other colleagues, other partners to join us in this endeavor. So we will have a lot to say. So I will just like to just welcome everyone and just like to just tell you that we have really top level speakers with us today. Some of them could not join directly, so they have sent us their talks by recording, and others will be joining us interactively. So let me just very briefly mention a couple of names that you'll be soon meeting. One of them is Mr. Ashraf Habibullah. I think most of you already know him very well. He's the founder and president of Computer Instruction Incorporated. I think Jennifer will introduce the speakers later, but I just, as a personal, because I know them very well, so I just want to thank them and welcome them to this event. And then, of course, we have engineer Ron Klemenzik. He's a visionary and pioneer and many things, and many people know about him. And obviously, we have Professor Murthy, a very, very good friend and also an accomplished academician and also a professional and involved in many development in building codes and so on. We also have Professor Penning, who's a key person in AIT, who has been working for a very long time on seismic and wind engineering. We will also be joined by some young faculty that were just joined AIT. Dr. Krishna, Mr. Ong, who's the head of AIT Solutions, and Engineer Boise, who's heading the largest construction engineering company in US. So I don't want to take away the introduction from Jennifer, but because I know all of these people so well that I think I should just say a few words of welcome and thanks to everyone. So we look forward to all of you joining this whole day, and I assure you that we will be having very engaging discussions from everyone. So thank you so much, Jennifer. Back to you.
Thank you, Dr. Naveed, for your welcome remarks and for making my life easier. Now let's all watch a video from a distinguished structural engineer who made a huge impact in his profession. This man need not any introduction at all. I'm sure many of you, if not all, know about this man who makes sure that structural engineering is known as a profession that saves lives. Of course, he is none other than Mr. Ashraf Habibullah, the founder, president, and CEO of Computers and Structures USA. CSI has been actively collaborating with AIT for nearly 20 years on many initiatives, including student scholarships, research, and development. Let's hear it from Mr. Ashraf.
Hi there. Welcome and greetings from California. I'm Ashraf Habibullah, and it's my incredible pleasure and honor to have this opportunity to address this AIT Tech event on the future-proofing of our built environment. I really love events like this because they highlight the incredible contributions of the structural engineering profession to humanity. Those that know me know that I have always believed that human beings are created for one fundamental reason, and that reason is to make the life of another human being better. And the beauty about the structural engineering profession is that we make life better for all of humanity on a daily basis. I mean, consider the stuff that we do. You don't have to look very far to see the incredible impact of our profession. Every metropolitan city is a testament to the grandeur of our work. And it's only because of structural engineers that our economic infrastructure even exists. On the other hand, our retrofit work preserves our past. It preserves our heritage. It preserves our history for all of the future generations to come. Every monument that's a testimony to the grandeur of humanity is standing only because at some point a structural engineer was involved. And above all, we are in the business of saving lives. We protect humanity from the ravages of natural hazards. Structural engineers are the reason why buildings don't fall down in earthquakes and buildings don't topple over in windstorms. You know, they say that a person becomes a hero by just saving one life. I contend that structural engineers are saving lives every time the wind blows. That is the grandeur of our profession. I'm really sorry not to be there in person, but I promise to be in Bangkok as soon as this pandemic subsides so we can party with this jacket. But until then, stay healthy, stay safe, and I look forward to being with all of you very, very soon. All the best, always. Thank you.
Thank you, Mr. Ashraf and CSI for the continued support to AIT. As Mr. Ashraf mentioned in the video, as soon as we can travel, we will welcome him to Thailand again for another big event. And we hope to see you all in person. Moving on, we have Mr. Ron Klemensic, Chairman and CEO of Magnuson Klemensic Associates, a structural and civil engineering firm with offices in Seattle and Chicago. Mr. Klemensic's work has been recognized by numerous awards, most recently as a 2020 inductee to the National Academy of Engineering. Other awards include being honored with 2019 Academy of Distinguished Alumni at UC Berkeley and the 2019 ASCE Outstanding Projects and Leaders Award. There are many awards, but I will not mention all of them. So his keynote for today is Beyond Concrete Core Wall Buildings, the Freedom of Performance-Based Design. Please welcome Mr. Ron Klemensic.
Hello, everyone. I'm Ron Klemensic, Chairman and CEO of Magnuson Klemensic Associates in Seattle, Washington. I'm honored and delighted to be with you today at AIT. Some of you will recall that I've presented to your group in the past. I very much enjoy visiting Thailand and Bangkok and wish that I could be with you today, hopefully this time next year. Today I'm going to talk a little bit about performance-based seismic design, as I often do, but today I'm going to focus on buildings that have reached beyond concrete core wall buildings, which have been the focus of the last 20 years of performance-based seismic design. So we're going to talk about the freedoms that might exist to design otherwise and focus on one specific building in particular. I come to you today from Seattle, Washington, a very far distance from Bangkok, but I send you warm greetings and again, hope to see you again in person sometime soon. As we design tall buildings, in particular in zones of high seismicity, we have to think about different ways of designing and the architectural challenges that are presented to us by modern architecture and how we might adapt our engineering principles through performance-based seismic design to realize these new works of art and architecture. Buildings such as this, designed by Lord Norman Foster in San Francisco with a perimeter exterior megaframe bracing system. This is something far beyond what we've done the last few years, or the last 20 years in fact, in seismic design, where we've primarily focused on reinforced concrete buildings, and in fact reinforced concrete buildings with concrete cores. In this case, this building has no core. It's a perimeter mega braced frame. Yet through the principles of performance-based seismic design, we're able to design this building efficiently and safely and reliably. The floor plan looks something like this, where the red color indicates the location of the mega bracing, and the blue color indicates some internodal bracing or minor bracing. This system overall was tested both at service level earthquakes and at maximum earthquakes to ensure the performance of the building was adequate and met all of the goals that we set out to. The building I hope to focus on with you today is this building in Seattle, Washington, actually just a few feet away from where I'm standing. It was just completed recently, and as chances would be, we originally designed the building with a reinforced concrete core. The owner of the building asked us to see if we could come up with a better idea, an idea that would save time and save money, and still use the principles of performance-based seismic design. In the case of this building, Rainier Square, we did such a thing, and I'm going to share the details of that system with you now. And it's only through performance-based seismic design that we're able to achieve this design, because it falls outside of any of the code parameters that we would read in the prescriptive language of the code today. The building itself was on the cover of Engineering News Record magazine a few years back when we first designed it, because of the novel system that was used, not recognized by any building code. There was many risks associated with that, of course. And performance-based seismic design allowed us to overcome those risks. In Seattle, it's located in the heart of downtown on 3/4 of a city block. The project participants were notable Seattle architects and developers. And here are some of the statistics of the building. It's a very tall building, nearly 300 meters tall, with 7 basements, 1.4 million square feet of space in total. A typical low-rise floor plate looks something like this, where the red color indicates the core wall of the building. Not dissimilar from what you'd see with a reinforced concrete building, but in this case, we're going to learn that we used a composite system, one combining steel and concrete in a new and novel way. As the building rises, the tapered shape of the building causes the floor plate to become smaller and the core becomes smaller as well. And at the top of the building, it's actually a square floor plate with residential units and a square core indicated here in the red color. In order to brace the building for wind and seismic loads, we needed to supplement a core with some additional bracing, in this case an outrigger system located at the mid-height mechanical floors with outriggers and belt trusses reaching out to outrigger columns. Again, all of this is fairly indicative and similar to buildings that have been built the last 20 years. And what's novel about this building is how we actually made the parts and pieces. A close-up of that outrigger floor with the outrigger trusses and belt trusses shows in a traditional sense we might connect steel trusses back to a reinforced concrete core. That connection becomes very challenging and very time-consuming, very costly. So we tried to imagine a whole new system. And that whole new system was entitled a concrete-filled composite plate shear wall, or a panelized system, in which prefabricated steel panels could be made in a shop, trucked to the site, and then erected to form the building much like Lego blocks form a Lego tower. Some of the dimensions of those panels ranged in thickness from 45 inches, which is about 1.4 meters, to 21 inches, which is just under a half a meter. The plate thicknesses you can see here in plan view are very, very thin. You see here a half-inch thick plate and a half-inch thick plate interconnected by rods in plan view. Those rods are spaced at 300 millimeters on center. Those rods interconnect the two plates, and the rods are connected via fillet welds or alternative connection methods, all of which are aimed to activate the full tensile strength of the rod in order to provide confinement for the concrete and stability for the panel. The splice connections were also made in this fashion, where one plate stacked on top of another plate, and in this case were welded together in the field to form that field splice. None of this system has been described in the building code until just now, and so as we were designing this building, we needed to use performance-based seismic design principles in order to justify the geometry and the design. Individual panels look something like this, where the link beams that are commonly formed in the field were actually prefabricated as part of this H-shaped panel, and those panels then trucked to the site and stacked on top of each other to form the building. In this case, we used 8 corner columns to form as guides for those panels. The corner columns were 2 stories tall, where the individual wall panels were only 1 story tall. Again, all of these pieces being fit together in the field with the prefabricated units. Research behind all of this system was conducted starting in the mid-2000s at Purdue University and funded by the Charles Pankow Foundation and the Magnuson-Klemensic Associates Foundation. Professors Bowman and Krager were the first to start to research this back in around 2005, 2006. Here you see a 5-story tall T-shaped wall section, which we built in the laboratory at half scale and then tested through the rigors of seismic loading protocol. We looked at the panels also in an unconcreted position to understand their buckling capabilities and strength in the erected position prior to any concreting. More recently, Professor Varma at Purdue has carried on with the research and his team, looking at a variety of panel configurations wherein the cross-tie geometry and or studs inside the wall panels help provide the additional stability. We built full-scale mock-ups to ensure that this building would be able to be built correctly and efficiently once we got underway on site. A full-scale concrete mock-up was first conducted to test the flowability and placeability of the concrete mix design. The mock-up was made of wood formwork and plastic cross ties so that we could take it apart after the concrete was placed to see how the concrete flowed and was consolidated to ensure and gain confidence that our mix design would perform as intended. We also built a steel mock-up to ensure that the pieces could be fit together, manipulated off the truck, lifted into place, and then secured. Those pieces were fabricated in a shop in Portland, Oregon, about 3 hours south of the site, Here you see one of the large corner columns being fabricated. The holes that you see in the side of the corner column are flow holes to allow the concrete to flow around the corner as it's being placed. Those panels were then stacked on trucks in Portland and shipped to the site in Seattle, where the erection team practiced their erection techniques, both tipping the panels off the truck and lifting them in place and then securing them in the proper position. You can get a sense of the scale of these panels as compared to the individuals in this photograph. They're quite massive. The field welds were also made as part of the mock-up to understand the best welding procedures to be used to secure the two panels together. Ultimately, shop drawings were prepared. Typical panels such as this, so just a planar panel, or more complex panels that included the link beams, as I mentioned, including, if you look closely, shear tabs to receive incoming beams, and the ledger angle to support the metal deck were all fabricated in the shop. Mechanical penetrations for ductwork and piping were also prefabricated in these panels to allow for a very efficient field erection process. Ultimately, the panels arrived on site and were trucked to a very close location and lifted down, in this case, into the excavation, where they were secured at the foundation level. In this case, the initial ring of panels was erected on steel columns, or we entitled them stanchions, that were embedded full thickness through the mat foundation, which was 12 feet thick, or about 3.5 meters thick. Those stanchions held the original wall panels in place while the reinforcing steel was set for the mat foundation. Here you see the mat has now been poured and the wall is ready to rise vertically. Panels began to show up on site immediately thereafter, and the building was constructed very rapidly, as you can see in some of these photos. From the beginning of construction to the end of construction, we erected 65 levels of steel in only 10 months. This is an amazing feat in order to erect a building of such scale in such a short amount of time. Here you see those 2-story tall corner columns that formed as guides with the 1-story tall panels interplaced between them. Looking closely, you can see round holes in those corner columns, and that's the location where the concrete was inserted and placed through a pump. As the core wall rose up higher and higher in the building, you can see some images of how the parts and pieces came together. This image actually is interesting in that it's looking directly out of my personal office window. My office is on the 32nd floor of the building next door to this construction site, so I was able to watch the construction of the entire building firsthand. A close-up of some of the wall panels coming together, and that connection between the outrigger trusses and the core wall was all shop fabricated, saving a bunch of time in the field. Originally, it was thought that these connections built in the field would take an additional 2 months. That 2 months of time was eliminated from the schedule through shop fabrication. The outriggers themselves were a combination of steel shapes. You can see here, and in the gray color, a buckling restrained brace. And that buckling restrained brace acted as a seismic fuse for the overall system. Once again, only through performance-based seismic design were we able to demonstrate the performance of this system and that it would achieve the objectives that we set out in terms of overall performance. The topping out ceremony occurred exactly 10 months to the day from the first day we set steel. An amazing feat, if you can think of that, 10 months to erect 65 floors of a building. The building's now completed. In fact, just recently the hoist came down, the exterior wall is completely installed, and people and residents and office workers are starting to move into the building. So again, only through performance-based seismic design were we able to achieve this type of new, novel, never been done before system through using the basic principles of engineering, math, and science. After the outcome of the design of that building, we've continued research on this and have delved into the world of performance-based fire design, testing these wall panels for their fire performance to understand whether or not they need to be spray fireproofed. The research has been completed at this point, and the outcome is that they do not need to be spray fireproof so long as certain design parameters are met. Subsequently, a number of new buildings are being built using the same system, given its promise of efficiency, resiliency, and speed, all being done using performance-based design technologies and methodologies, both for the structural engineering and for the fire engineering. This building is in San Jose, California. It's about 20 stories tall, and in the red color, you see the core wall layout here. Once again, very similar layout as if it were a reinforced concrete building, but in this case using the composite plate shear wall sandwich system. The mock-up that we built for that building was completed not long ago, and that building is called 200 Park in San Jose, California. Here you see one of my colleagues, Russell Larson, standing adjacent to the foundation connections for those panels, again, sitting on these stanchions that anchor the wall panels into the foundation itself. Currently, we're designing this tall building in Boston, our first attempt in a wind climate outside of a seismic zone to use this same performance-based approach, in this case, performance-based wind engineering, in order to justify a system which has very similar parameters, but in this case, using a bolted field splice. In many locations throughout the world, welding is not viewed as particularly field-friendly, and instead, bolting would be a much more preferred approach. So we're investigating and designing bolted splices for the field. Again, using performance-based seismic design and performance-based wind design methodologies supported by research at various universities. And here you see some of the details of the proposed bolted splices. Rounding things out, we're currently designing other buildings as well. This is a 3 million square foot development, once again in San Jose, California, that uses a combination of the composite plate shear wall panels as well as buckling restraint braces. So you can see novel arrangements and unique, not prescriptive systems that are being used in a variety of buildings throughout the US and in fact throughout the world. And lastly, a few buildings in Oakland, California, where once again, traditional core wall looking buildings using performance-based design methodologies to realize systems that include core walls and in these cases, perimeter brace frames. I hope I shared with you today a few insights into other systems that can be realized using performance-based seismic design methodologies and extend that to fire engineering and wind engineering, which are areas that are new and expanding as we speak today. Again, thank you for inviting me to participate in the conference. I wish you all very well and hope to see you again very soon. Thank you.
Thank you, Mr. Ron. We will be delighted to welcome you in Bangkok again. Hope to see you in person soon. Now it's time for the keynote of our very own Dr. Naveed on developments in structural engineering software and technologies. I'm sure most of us here know that Dr. Naveed has led several structural engineering and software developments in his 35+ years of experience, and also has been teaching several courses and supervised researches focusing on new trends and technologies in structural engineering and software development. May I invite again Dr. Naveed?
Yes, thank you so much, Jennifer. Let me share the screen. Let me know when you are able to see so I can start the presentation. Okay, all right. So first of all, let me once again thank Ron for that wonderful presentation, because he has given us a very practical view of a major development which has taken years to develop. And these are the pictures, these are the things that you hardly get to see. This work has been published in many places, but the kind of details that we hear from him directly is really amazing, and it sets a new direction on how the tall buildings will be constructed in the future. And in fact, when we saw that development being done at AIT, also we started a few theses on how best we can model such walls which are composite with steel and concrete inside, and we looked at various techniques, and that's another area that we are working on. And also he mentioned about the wind performance-based design. That's another area of interest for a lot of engineers, and with the climate change and all that is happening, this will become even more important, and that's another area that we at AIT are looking at, and I'm sure we will get a chance to talk about that later in the day. But right now, I want to talk about some of the things about the advancements in technology and also in structural engineering that must come together, or that are coming together to make the infrastructure future-proof, because that's the focus of the talk today. So let me start this discussion by, first of all, re-emphasizing what has already been mentioned by Ashraf very clearly. And he said that we can't have economical development without the built infrastructure. So built physical infrastructure is the backbone of the economy and the society. Everything that we see here is part of the built environment. In fact, when we look at the development of the civilizations, one of the things we look at is how well the infrastructures were developed, which includes building and roadways and transportation and other network and waterways and things like that. So the built environment is essential for any economy to develop and any society to progress. So that is quite clear that the built infrastructure, physical infrastructure, is an integral or important part of our society. So having said that, or having established that, then we see that the structural engineers are actually at the backbone of the built environment. So we have also seen from Ashraf's talk that how structural engineers contribute to the design of buildings, bridges, tunnels. In fact, anything that is ever built physically, structural engineers have to be involved in some way or the other. It could be, or every other discipline, every other development, every other infrastructure, that even the telecommunication infrastructure requires structural engineers to design the physical components of those infrastructure. So even if the data centers are being built to store the data centers have to be designed by structural engineers. So there's nothing that can be built unless the structural engineers design it. So structural engineering, civil engineering is the backbone of the physical infrastructure development, which is the backbone of the economic development and the society. So we have a really crucial role to play in this whole development. Now the question is, how do we do future-proofing of what we do? So future-proofing, if you look at this definition, is actually the process of anticipating the future and then developing methods of minimizing the effects of shocks and stresses of the future events. In fact, that's what we do. Structural engineers always are thinking ahead of what will happen to a building, in the next 100 years or 50 years of its life, what loads will come onto it, what can go wrong, and try to predict it and then design against it or prevent it from happening. And that's what we do on a daily basis. But we don't really think of our work as future-proofing, because now the things are changing at a faster rate than in the past. The climate change effects and many other things are coming up. So because of that, we have to probably explicitly think about future-proofing our design, not just doing the design on a regular basis. So the role of structural engineers is actually, as I mentioned, is very important in the infrastructure development, and infrastructure future safety or future-proofing is also our responsibility. So we have to help make the physical infrastructure future-proof through our work. And that's what we are just discussing in this whole event. And what Ron mentioned is another important aspect of how we can make better, taller buildings, which is safer, and we can design them for greater hazard levels that we anticipate in the future. So what makes a built environment future-proof? Obviously, it remains to be serviceable for a long time, for its entire life. In fact, we normally say the building life is 50 years of structure, but the main infrastructure needs to last much longer. It needs to be always safe. And this is a topic that we will talk a lot about this day. It needs to be resilient. And as you know, resiliency goes beyond safety, and it's a concept beyond just being safe. It talks about a lot of other things which go after being safe. So it has to be resilient, and it's resilient also, it lends resilience to the economy, to the society, and so on. It has to be flexible. It should be able to change with the future needs. It should be adaptable, adapt to the changing guidelines, changing rules, and changing new developments. So it has to be adaptable from that point of view. It has to be sustainable. Environmental sustainability and all kinds of sustainability has to be built into the design, and it has to be dismantleable. In the end of the life, it has to be, we should be able to take it down safely and with minimum loss of the resources. So all of this, if we consider that in the design explicitly or implicitly, we are making the built environment future-proof. Now, for the structural engineers to be able to do that, we have to continue developments in structural engineering, like the one we just saw, lab testing, 15 years, 20 years. It took a lot of time to develop a new system that will continue, and that similar things goes into methods in processes. Then, so that is the development in the structural engineering field itself. Then is the other developments going on which are outside structural engineering or civil engineering. We have to make sure that we bring them in and we integrate those emerging technologies with our structural design process and take the best advantage from everything that is happening around us. We cannot just only focus on our field. We have to see what are the things that are happening, what other people are doing, and how we can bring them in. And obviously, we need to develop tools and software that use these technologies to the best and put them in practice and make them practically applicable. So we need a basic development in our own field. We need to make sure that the other technologies are brought in, and then we need to put this whole thing into software and tools that we can use and effectively and apply them. So that's typically what structural engineers are doing and are to be doing. Let me just briefly give an overview of where the structural design approach is going. And a long time ago, people used to start by intuitive design. There were no design code, there were no computers, there were no calculations. People just had a good intuitive sort of sense, and those master builders will design many things. And then after that, the building codes came in and they codified many things. They gave us told us what to do, what not to do, how to do. And so there's a whole discussion on code-based design. And then from there, we moved to performance-based design, as Don mentioned in his presentation, and then we will talk more about this later. So performance-based design now comes in, which gives us a more explicit way of developing new systems which go beyond the code. And after that case comes risk-based design, which means that we talk about the risk explicitly, which is more than performance. And this also looks at what happens if the performance is not met. And from that, we move to resilience-based design, how these decisions will make the structure resilient. Resilience goes beyond structural safety, it goes beyond structural damage, it goes to human loss, it goes to cost of infrastructure or building not being used, and so on. So it's resilience design, and then that will lead to, or that leads to, explicit future-proof design where we have requirements for each of the future aspect to be considered. So that's how the structural design process is developing, or is ongoing, as we can see. And then there are emerging technologies which are happening all around us, and we use them all the time in our work. Artificial intelligence, 5G and Internet of Things, serverless computing, biometrics, augmented virtual reality, blockchain, robotics, natural language processing, quantum computing, and you name it. There's so many things happening. And I will just be showing a few of them very quickly and see how they can help in our work and help in making the structure and infrastructure future-proof. So the role of software in all of this is very, very significant, because all of this can't be done by hand anymore, as some of us who are old enough to remember the use of hand calculations and slide rules and things like that. Those days probably aren't coming back. So we have to rely on computers and computing and software and tools. So that means anything that we do ultimately will have to be part of some software. So we need to have software that support the design process. We have to help integrate emerging technologies into the process. So I'm talking about the software development process itself. People who develop software, they need to do this. They have to help simulate lab-based testing and future scenarios. In fact, a lot of the time, if you look at the research, it's a two-part research. The one part is lab testing and one part is simulation. And we try to bring them together so that the simulation is reliable and it can be based on lab testing, just like the development we just saw, where lab testing, mock-up models, and everything that led to software to be used for the final design. The final tall building was not tested in the lab, was not a mock-up. It was designed based on the simulation that was possible because of the software that was developed. And then software also helps us to visualize the enormous input and output in a multi-dimensional environment. So that's the role of the software, and we all know how important that has become. Now, there is the purpose of technology should be very clear. This should be basically to make the process easier and more efficient. That should be one aspect of technology. Technology cannot be used for the sake of technology. It needs to help something. So it has to help the process to run faster or more efficient, and also give us the ability to create a better system. That means not only to do what we do better, but also to do something new that we couldn't do before. So that's the right purpose or right use of technology in the end. It's a tool. So we should always see how the technology can be most effectively used to make what we do better, and also to create something which is better. I'm going to run through very, very quickly a few slides just to show you, typically what are the key technologies. I'm sure everybody attending this event knows about them. Artificial intelligence and the machine learning is, we hear all about always they're taking over the world, and with the robotics, and we have so many, good and bad things coming out of it. People are talking about the statics. We're talking about all the other things related to that. But the reality is that both AI, machine learning, and robotics are going to change things significantly for the things to come. Artificial intelligence, machine learning, deep learning, they're all phases of development starting in the early 50s, and now it's going on, and this will just continue as you can see. So we have got to make sure that we bring this into our workflow, our process. Then big data, again, it is said that we create and use more data. We create more data in one day than it was created in the entire human history before the last century. So there's a large amount of data being created everywhere. And then a lot of tools to dig, search, utilize this data, data analytics, data mining, so many terms are there. And we talk about big data. So everything, as you know, is now, because it's digitized, it's data and it's available somewhere and it's going to be connected. So we have got to learn to utilize the data that has been created. It's experience. It's a cumulative experience of billions of people, of billions of hours of and man months, person months. So we need to build upon that. So if we can make use of the big data, that will be really great. Sensing technologies, we have now sensors everywhere. Even a small, a cell phone has like 20 different sensors. A watch has, so many sensors. Sensors are everywhere. And those, we have got to make sure that how we can utilize these sensing technologies and sensors to the best advantage. You have temperature, humidity, air, motion, acceleration, light, magnetic field, sound, GPS. All kinds of sensors are available very cheaply everywhere. And they are installed in so many places. The challenge is to get the data from them and make sense out of them and see what information, what signal that they're sending is something that we can utilize. Quantum computing, as you know, is going to change the way that the entire computing is done, from 0-1 base to something in between. So that quantum computing is a completely different way. It can solve problems that have never been solvable, theoretically not solvable by computers, by classical computers. So that's what we are looking at, and we should be ready to sort of embrace the quantum computing when it becomes more accessible. Blockchain, we have heard a lot about that, and this is especially something that people think about. It's a reliability, it's a trust thing. So for the future proofing, I think the reliability of the things, and to be able to trust something and to be able to document something which is completely verifiable, is something that the blockchains can really help us to do. How can we bring more blockchain into our process, into the development of the infrastructure? Already many applications are there in many fields, and even in our field, people are looking at how we can use blockchain to tag things and then monitor or track those tags or track those events. Drones, as you know, everywhere the drones are there. They're there for delivery, they're for imaging. So, and they are now becoming more easier to use, cheaper to use, and so on. So we should see how the drones can help us. And I'm going to show a few of the examples. Construction automation is another area where the robotics are now getting more into the construction. Bricklaying used to be, as you know, a typical way that humans would be very good, or have been very good at since the beginning of the civilization. And now the robots can do that, if not better, just as well, or maybe faster. So this robotics and automation in construction is something, again, that we should embrace and make it part of our process. 3D printing is another part of the construction automation. Recently, many 3D buildings have been completed, and this is not only going to impact the way the buildings are constructed, but also the way they are designed, the way the detailing is done, the way the process is completed. And so this whole process of automation, 3D printing, and all of that will also impact how the future infrastructure is built. IoT is like a culmination of many of these things, because it gives us the ability to connect everything together. So the Internet of Things is a way to basically connect all the disparate things that I showed earlier and make sense out of that. So this is already being used extensively, and sometimes we don't even know it, that IoT is being used, but definitely as a field itself, IoT has a great potential because it helps us to integrate many things together and bring them into one platform or one framework. Smartphone, as you all know, is actually a way to access maybe majority of these applications. And someone said that if your future development does not involve a smartphone, your development has no future. This is an exaggeration, but it's true. A lot of the things that happen these days, somehow or the other, the cell phone is involved. Look at the pandemic management and everything. Tracking is done by the cell phones, and then we have QR codes. We have this. You can just basically track anything because everybody has this device which has so many sensors, which is connected to the internet. So the IoT is there, the sensors are there, the data mining is there, the AI is there, and imaging is there, and visualization is there. So everything that we need is available to us. So if our design process, our work also includes this device as part of the work, it can just make things better. So now we are looking at a convergence. That means things are converging. Structural engineering and technologies and IoT and other things, they are coming together, not only in our field, in every field. Medicine, for example, is way ahead of everybody else. In fact, most of the new technologies first get into medical applications and medicine. So robotics are over there, the 3D printing was over there, imaging was over there. So similarly, structural engineering, we are looking at the health of the infrastructure. So we could also learn from what the medical profession is doing by rapidly, absorbing the new technologies. Smart cities is one example of that, when things come together in a larger scale, when everything converges, and then you can bring this whole thing together, open data, culture, standards, infrastructure, smart buildings, IoT, retail, energy, mobility, citizens, everything comes together, and then smart cities are created out of that. And then there's so many aspects of that. And obviously engineering, structural engineering, civil engineering is a major part of developing these new ways of building our cities, which are also designed to be future-proof. So let's come back to see how these emerging technologies and structural engineering actually can match with each other. So I'm going to just give you some very brief introduction to this one. First of all, we should recognize that there's a paradigm shift. Earlier, when the computers came in or the technologies came in, we used the computers or technologies to automate the existing process. So we just, whatever we were doing, we tried to make it work better. But now, at this point, the processes are developed that are based on technologies. That means we have to think differently. We have to think, what can I develop which will use these technologies rather than use a technology to make something that I'm doing better? As I mentioned earlier, the purpose of technology is both. So we have to see how the technologies that are coming up, we can use them to make things better, not just make what we are doing faster or better. The life cycle approach, of course, is always the right way to start. We should see where we can apply these technologies from the conception, planning, design, modeling, analysis, design, detailing, construction, operation, and end of life. So if we look at the technologies in each one of them, then we will be able to see what technology is most suitable for what aspect. And I just try to make some rough metrics of how these things will mesh together. So first of all, let's look at the development in structural engineering and its relationship to future proofing. So I mentioned earlier that the structural engineering design process is developing: intuitive, code-based, performance-based, risk-based, resilience-based, future-proof. How does each of that relate to various aspects of future proofing is what is shown here. And we don't have time to go into all of that, but you can just see the darker color means that there is more relevance. Lighter color means there is less relevance or there's less application. And these are just based on, very intuitive kind of a linkage. So we can just see that the performance-based design is heading towards higher application. Resilience-based design even more. And if we do future-proof design, then it will be more related to future-proofing. Similarly, we can look at the technology application and structural design process. And again, different technologies, AI, data analytics, big data, virtual reality, mixed reality, augmented reality, IoT, blockchain, robotics, drones, and how they relate to various aspects of our design work. And you can see here that AI, data analytics, VR, and IoT, they all have a lot of relevance to various parts of the work, various aspects of the work that we do. So especially you can see in planning, AI could be very useful. Data analytics would be very useful for monitoring. IoT could be really very useful. So this is just a quick way of what is the relevance of these technologies to what we do and which one are most relevant to that. And then this can be used as a rough indicator of where the development is focused and can be focused. Similarly, we look at technology applications to future-proofing, how each technology will help for the future-proofing. And again, you can see IoT and as well as data analytics may help a lot. AI in some areas, blockchain may also help in some areas. So again, this is like I mentioned, this is a rough metrics. Other people may be looking at it in a different way, but this is what I look at this point and how the technologies have a relevance to the future proofing of the built infrastructure. Something about AIT and the same metrics. I would like to show what AIT is doing in this respect. So AIT, design, development, and future proofing. So the dark areas are where our research is focused on. So you can see performance-based design is one area. We're doing a lot of work there. We're also doing work on resilience-based design and also in risk-based design and others. So that's some of the work the structural engineering group especially is doing at this point. AIT technology and design process, as you can see here, we are working on the application of the virtual reality, of AI, of drones, and IoT in various areas. So this is some of that will be talked about today in our afternoon sessions. technology and future proofing. And again, so the work that we are doing at, as you can see, AI is some, IoT is some, and then some area in blockchain and some data analytics. So this is some of the areas where there's research ongoing and planned for the future. And this is an area where our students and our researchers are looking at how we can bring in the technology to make the structures infrastructure future-proof. So I'll just present a few of the theses from our students very briefly, just the topics. So you can see, like, for example, using data analytics approach to estimate the efficiency of structural design of tall buildings, and we can develop the rating system. So there's a new framework developed recently by one of the students here. Then calibration of structural models using measured building response. So that's related to how we can calibrate building response and models that we make with the actual buildings that are instrumented. So we can bring that back and we can instrument and make our models much more reliable. Image-based inspection and monitoring of tall buildings. For example, you can use drones and other imaging techniques to detect cracks and to monitor them. So that is another area that the students have worked. Enhancing seismic resilience of non-structural measures for tall buildings in Manila, for the Philippines, for example. So some researchers look at how we can take the buildings and make them more resilient by looking at the non-structural damage in a particular country, and this is the framework that they use. This is artificial neural network-based approach for the seismic fragility analysis of highway overpass bridges. How can we use the artificial neural networks for example, generating the fragility and the reliability of the bridges, and so on. There's a lot of talk, in fact, on fitness and personal health at this point. Many of us wear these devices or watches or smartwatches or fitness devices that monitor everything that we do all the time. For example, they monitor the heartbeat and heart rate and so many things. And with using a few sensors, they can tell us what's happening with our body, and it can help to make our body, plan our health and make it better for the future. So same thing can be done for buildings as well, as you know. So networked structural health assessment and post-earthquake response of tall building is another area that we are working on, where you can use the sensors placed in the buildings and bring them together and monitor them all the time to see how they are performing and what is the future expected performance. So this is just the framework for that smart system for post-earthquake assessment. And this is something that we are working on in Philippines to implement on some of the buildings. Drones, I mentioned again. So this is another interesting project where the drones are used to actually take images of an old fort, which is about, I think, 700-year-old, create a 3D model, convert that model into a finite element model, do the assessment, do the seismic hazard analysis. So because the physical measurement of this fort is difficult, so you use drone imaging as well as you use the internal the LiDAR imaging to create the 3D models, and from that you can go back to creating finite element models. So this is now possible by using technologies of this kind. You can also use multiple technologies. In this project, we use 3D printing, we used wind tunnel testing, we used performance-based wind analysis, we used simulation, we used many things. We used drones to basically look at the design and construction and other aspects of a dome. So this is another area, example of where the various technologies can be used. Smart monitoring of construction project using drones again. So you can use drones to monitor the construction progress, and then you can compare it with the BIM models to see how much work has been done. So this is a sample, on one of the project, you take the drone images, you take the BIM model, then you combine them to see how much progress has been done, because both of them are on the same three-dimensional space. So things like this can be done for monitoring of construction as well as for accuracy and so on and so on. That brings me to the development of the building information modeling and bridge information modeling, which takes the design to multi-dimension, not only consider length, width, and dimension, also consider time, construction time, and what happens over time, plus the cost, plus the sustainability, plus the management after construction. So this several dimensions of BIM are possible because all of the data is integrated at the same time. So design can be done and we can take it to different levels. and it can lead to integrated digital delivery systems beyond just analysis. That means we integrate all of the thing from the beginning to the end. Like I mentioned, the whole life cycle can be integrated into this digital delivery system. And Singapore is doing a lot of work on that. We're also helping on parts of that, working with that, with the Singapore authorities. Software, as I mentioned, software are now also, a lot of software being developed. I just mentioned a few from CSI because we are a part of the team developing that. And CSI is also, as we heard, has been working with, it has been supporting many of the events, and AIT and CSI have collaborated for over 20 years. So I just mentioned a few software that they are developing, and all of that is directed towards many technologies that I already mentioned. Cloud-based computing, for example, or having this cloud-based access to models and to be able to do things remotely is another area that will be useful, as I mentioned, having mobile devices connected to the models. So having said all of that, and we can see now that the technologies, robotics and AI and so many things are absolutely encroaching upon many things that we do, whether we like it or not. So the best thing is to embrace them in the right way. And as I've shown you, there are so many opportunities that we can use technology, and we can use them for good. Of course, technology can always be used for negative aspects also, but I'm sure as engineers, we always think about the positive aspects. As Ashraf said in the beginning, we want to make people's life better. So for that way, we have to embrace energy in the technologies in our field. But some people might say, will the technology take my job? Will I lose my job if everything is done by AI and robotics and computers? So this is just a light note ending my talk. And there's a website called Will AI Take My Job Away, or Will Robotics Take My Job Away? And if you go to that website and you enter, if your job is accountant or auditor as your job, then it will say that, yeah, 95% chances that your job will be automated by AI and computers in the future. And you say you're a computer programmer, it says 48% chances that your automated computing and automated software development will take over your job. And that's really happening. The software engineers are so good that they're writing software that writes software and putting themselves out of job. But if you enter civil engineering, there's only a 2% chance at this time that your job will be completely taken over by the computers and robots. How true that is, I'm not so sure. But this is, just an indication that at this point we are still safe. But we have to make sure that we embrace all the technologies, keep developing, keep innovating, and make sure that our jobs and our relevance remains so high in the future as well. So with that, I would like to thank everyone for this. And then we have in the afternoon, we will be discussing many of these things. So thank you so much. Jennifer, back to you.
Moving on, may I please welcome Professor Penang Warnichai. Professor Penang is a professor in structural engineering at AIT. Besides his association with AIT, he has been part of various significant elective and appointed offices, both in Thailand as well as in the region. Some of Professor Warnichai's current professional affiliations include Scientific Board Member of the Global Earthquake Model, Member of the National Earthquake Committee of Thailand, Chair of Chapter on the Effects of Earthquake and Wind Loads, Engineering Institute of Thailand under His Majesty the King's patronage, Member of the Civil Engineering Chapter, Engineering Institute of Thailand, under His Majesty the King's patronage. Professor Warnichai has considerable experience when it comes to the conducting research projects in the area of seismic hazard and risk assessment. May I invite Professor Penang for his talk on the recent research studies at AIT on earthquake engineering, vibration control, and structural health monitoring.
Thank you, Jennifer. Can you hear me well?
Yes, sir.
I'm going to share my slide.
Yes, sir.
Okay, let's start from the first one. Can you see the slide? Okay.
Yes, sir.
Can you see the pointer as well?
Yes, sir.
Okay, good. I think we are ready to start. Well, my talk will be about some research study we are doing at AIT. well, similar to what Dr. Navid has presented. But I'm going to focus on earthquake engineering, vibration control, and structural health monitoring. Let's begin with vibration control. Okay. Let's see the next picture. This is an example structure that needs vibration control. It's a very tall, slender steel structure, steel stack. Actually, this structure is located in Rayong, about 200 kilometers from Bangkok, the capital city of Thailand. And the structure is quite tall, about 80 meters. Because it's made from steel, it's quite flexible. And you know, this type of structure is very vulnerable to dynamic wind effects. The wind load can produce a shaking force that can shake the structure. It will create a large displacement as well as bending stress. It may lead to fatigue failure of the structure at the base. This slide shows you the top view of the structure. You can see the yellow circular section, that is the stack section. And you can see the arrow showing the wind approaching this one, and it's created vortex flow behind the stack. The vortex is a kind of periodic vortex, and it's produced periodic change in pressure. This wind pressure actually creates the net force. The net force represented by red arrows. Well, this arrow is kind of swinging arrow. It's not static force. It's the magnitude and direction change all the time in a periodic manner. So this one created both the deflection in along wind and in a crosswind direction of the stack. It's a kind of producing a shaking force to the structure. Now you can have try many approach to prevent the dynamic effects to this tall stack. This is one way we call aerodynamic approach. You can modify the top geometry of the stack, putting what we call helical strake, wrapping around the stack. This actually will destroy the correlation along the height of the vortex shading. It will weaken the force, and it will reduce the dynamic effects of the wind load. Actually, this is quite popular approach. When we test a small model in wind tunnel, this approach proved to be very effective. But in a real scale, we are not sure. Okay, I have seen many reports, but the reports are quite conflicting to each other. Some say that it's quite effective, some say that it's not. So I don't know which one I should believe. But anyway, this approach has been widely used in practice. That's one way. Or you can try what I call it here is a structural engineering approach, because we are familiar with strength and stiffness. So this, to prevent the dynamic effect, we actually stiffen the steel column, the stack by putting in the stiffening truss 3D. That is a structural engineering approach. There's another approach which I want to highlight. I call this structural dynamics approach. You can see here, actually no stiffening truss, no helical strike, but we put a kind of the blue color ring here on the top of the stack. It's become like a ring pendulum. Okay, from the distance you cannot see that, but if you zoom up, you can see this blue steel ring hanging from the stack. Okay, that's how it looks like, the steel ring. You can see here, the weight is about 3 tons. and is hung from the stack by these suspended wire ropes. We have 3 ropes hanging this pendulum so it can swing in any direction. Okay, and the bottom of the ring is connected to the stack by viscous damper. We actually purchased this unit from Germany, and we actually put them together to form a pendulum system, and we call this Joule mass damper. Okay, it's a kind of vibration absorber. When the stack vibrates or sway, it's going to make this pendulum move. Energy is transferred into this pendulum motion, and energy in the pendulum is absorbed by viscous damper. This is a way to increase the energy dissipation of entire structural system. Okay, but in order to make the system effective, we need to make this Joule mass damper, the frequency of pendulum, match with the natural frequency of the stack. That's why we call this Joule mass damper. Well, this is the Joule mass damper I designed by myself and installed it about 20 years ago. Now we are looking about this concept. You can see that it's not only applied to steel stack, but it's applied to many other structures, including this famous structure. This is a super tall building in Taipei. I think everyone knows, anyone that visits Taipei will know that they have one very super tall building called Taipei 101. Okay, and if you look at the structure at the top, you will see the structure has a large pendulum hanging on the top. This is a really big size pendulum. The mass of this pendulum is several hundred tons. It's hanging by a pendulum arm, pendulum rope of about more than 10 meters long. It's occupy many floor space. They install this pendulum just to use them as a Joule mass damper for this super tall building to suppress the wind-induced vibration, as well as it may help in reducing seismic response as well, but not as much as wind. Okay, but if you look at this, if you look at the pendulum size and the space is occupied, actually I can say that this pendulum type TMD is quite effective, but it's actually occupy a lot of space and it's quite hard to construct. It's quite expensive to construct the structure that carry this pendulum. At AIT, we are thinking of a different idea. Okay, a different configuration of Joule mass damper that looks like this. We call this a Joule mass damper that made from multi-stage steel laminated rubber bearing. It's a very simple construction. You know, you have a mass put on rubber bearing, and this rubber bearing actually is a steel laminated rubber bearing. You can find this bearing in some bridge structure. We are also, but it's quite a thick rubber bearing, and we put it in many stages. We found that this type of configuration is possible to design very large mass. We can make it very long period, long natural period, and it can deform with a large displacement. It occupies only small space. The construction is quite simple. You just put it on the floor. No need to hang it from any structure. It's low maintenance requirement because this rubber bearing is quite durable and the cost is low. And rubber bearings are quite available in the market. Now, if you come back to Taipei 101 tower again and look at this kind of large pendulum structure, if we redesign the June mass damper, it can be reduced to something like this, much smaller, much more compact. And you can actually use the space on the top floor for other purpose. This is very expensive space. And if you do it this way, you can save the cost, reduce the cost of the damper, and you can make it more economical and practical. We can apply this the same type of system in many other buildings. So this is work done by one master student at AIT, Mr. Pruk Jansukho, just a few years ago. We actually construct the prototype scale down model of this June mass damper. The mass is just 2 tons, 2,000 kilograms, put on a small rubber bearing multi-stage. And we actually use a small shake table to simulate the top floor motion of the building. You can see here the movement. So we actually put the vibration sensor to the shake table.
อันนี้คือเป็นโหลดที่
that is his voice.
sensor displacement จาก across บนอาคาร
Okay, and we put the sensor to the mass. Based on this measurement, we can create a mathematical model for this June mass damper. Well, it has some nonlinear effect we call softening effect. We have never seen any report on this nonlinear effect. But since we conduct the test by ourselves, so we have this model that can accurately describe the motion. Okay, this is a work of another student that follow after Mr. Pruk. This is a work by Mr. Chanon Chodmani. He's still working on it. But his assignment is to see how we can implement this type of damper to the full-scale structure. So the first step is to design the full-size June mass damper. This time is not 2 tons, but is 1,000 ton mass put on many rubber bearings, arranging in a multi-stage. So it will occupy bigger space, and we cannot simulate, we cannot create a physical model, it's too expensive. So we just conduct the numerical analysis using computer software. So we are thinking of a 200-meter tall buildings installing this June mass damper. This is the result. We put a June mass damper of 1,000 tons on the top of this 200-meter tall building. Before we put the damper, this is a time history of horizontal acceleration of the top floor. The gray color. It shows very high level of floor acceleration. It's up to the level that can create many problems to building occupants. But after we install the June mass damper, it's reduced to the black color. So we can reduce down the acceleration level significantly by installing this compact multi-stage rubber bearing June mass damper. Here is another view from the top. On the horizontal axis show the X direction acceleration, on vertical axis show Y axis top acceleration. The gray color is the acceleration level without June mass damper. The green is the one with June mass damper. So you can see that we can significantly suppress the vibration response of the tall building if we have such June mass damper. Well, I'm hoping that some of you will be convinced and we can actually install this type of damper in real building soon in the future. And now I'm changing the subject to earthquake. This is an example of a reinforced concrete school buildings in Chiang Rai in northern Thailand. In northern Thailand is kind of have some seismic activity. We have some active fault, seismic source. And recently in 2014, we have a moderate earthquake in Chiang Rai. It caused damage to this building. This building is a very typical school building in Thailand. And it has one typical feature that's quite obvious, what we call soft story. You know, the first floor is softer than the upper floor, because upper floor we have many brick wall, brick panels, parapet wall. The first floor is open, just column. So the first floor is much softer than the upper floor. This is not a good feature. We call this irregular feature, and it's leading to the concentration of damage of earthquake response to the first floor. The damage will concentrate to the columns in the first floor. Okay, this is the investigation of the buildings after the earthquake. We saw the crack, the yielding, the damage to the columns. Okay, if the shaking is stronger, this building would have been collapsed, but it's still standing for this case. But we want to prevent this type of damage in the future. So this lead to another project. This is a seismic retrofit of a soft story RC buildings in northern Thailand using a buckling restraint brace. You know, the black color brace here and here. It's a collaboration work between AIT, Nanyang Technological University in Singapore, Dr. Lee Bing, and I work with Dr. Sutat from King Mongkut University of Technology of Thonburi. So we work together and we actually retrofit 4 buildings in northern Thailand. Now I'm working with National Taiwan University to retrofit 2 or 3 more in Thailand. So this one is actually the picture of buckling resistant base. I think you have seen the picture of buckling resistant base in earlier presentation by Dr. Ron Kremenczyk. Buckling resistant brace is a brace that can yield and plastically deform in both tension and compression. It will not be buckle. It's buckling restraint. So it can actually absorb vibration energy effectively, both in tension and in compression. I mean, building can sway in any direction. It will absorb energy through his hysteretic behavior. Okay. Well, this buckling resistant base is homemade, made at our lab here. This is our structural engineering lab in AIT. We create the full-scale model of this brace. We put it under the loading frame, apply the actuator, we pull, push, apply the kind of cyclic load up to the level of yielding to create a significant plastic deformation. And the brace actually work well. You don't need to put so many brace into the structure. For example, in this building, you just put it only 4 brace in one direction and 4 in another direction. And the cost is not that high. The cost of retrofit by using buckling resistant brace is about 50% of the building cost. Not 50, 15% of the building cost. It means that if you have the budget to build a new building, you can use this budget to retrofit about 5 to 6 buildings, 5 existing buildings. Okay, so it will be a better use of the money. You can retrofit 5 to 6 or 7 buildings using the same budget to build a new building. Well, this technique is quite commonly known and used in some countries, like in Japan. but it's still new for Thailand. This is probably one of the first building in Thailand, and it's new for many countries in Asia. I actually think that we should try more, especially those in Philippines, those in Indonesia, or from Nepal. These are earthquake countries. From India, north of India as well. You are in a seismic hazard area. So I think applying this technology will improve the safety of your building. We should promote more of the seismic retrofit of weak concrete structure. Well, moving on to other techniques. This is called seismic-based isolation. If the building is built from a lock to the ground, and the ground is shaking, it will create a very large impact to the building, not only to the structure, but also to the contents inside the building. But you can actually isolate that effect by putting the building on rubber bearing, or we call base isolation bearing. This is how it looks. This is a base of the building. We put the rubber bearing before, and we construct the entire building on top of the bearing. The bearing, as I showed you earlier, is a rubber bearing with a steel laminated. Okay, this is a kind of a standard bearing for base isolation. There are many types, and they are commercially available. Okay, now this is a project work requested to us by Public Work Departments of Thailand. They want to study the feasibility of this technique in applying to public buildings in the northern of Thailand. So this is a example building we call case study building. It's quite a large building, but it's a mid-rise, 5-story. And we set it as a thesis topic for one master student, Acharapan. She actually was assigned to redesign this building by putting the entire building on top of base isolators. So at this yellow color, we replaced the foundation. We put the isolation bearing underneath the building. So she has to look at commercially available bearing, and she actually select 5 different types of the bearing. We call group 1, 2, 3, 4. Put them underneath many columns, almost all the columns. This is a table showing the property. This contains a lot of details, but I want to highlight this one. KV is the vertical stiffness of the bearing. KH is a horizontal stiffness of the bearing. KV over KH, this ratio is about 1,000 to 2,000. That means the vertical stiffness is much higher than horizontal lateral stiffness. Well, in other words, the horizontal stiffness is very low. So the bearing is very soft in lateral. Bearing is very stiff in vertical. The stiffness in vertical direction is similar to the stiffness of the column of one floor, approximately the same order of magnitude. So this one show how we actually, this one show first the building without bearing. We show the animation of how the structure move under the earthquake. We call design basis earthquake. Well, the structure will not move this much, but we actually magnify the movement by 70 times so that we can see clearly how the structure moves. And the color show the level of damage. When you see the red color, means it's completely damaged. If it's a yellow or green, it's still light damage or moderate damage. Okay. But the structure will be extensively damaged if the foundation is fixed to the ground. Okay, and now we look at the case where we put the base isolation underneath the building. This time, actually the damage will be much less, and the structure move more at the base. This is a base isolation element in a computer model, so it's moved laterally. Okay, you have to design the building so to allow this kind of movement, relative movement between the foundation and superstructure. So the movement concentrate at the base isolation, and the structure still deformed, and it still have some damage, but the level of damage, the extent of damage is much less compared to the case with fixed base. So I think you can see the potential. This simple technology can be applied. Okay, if we design well, it can prevent many problems, suppress many problems. Okay, the idea of base isolation can be applied to tall buildings as well. And in Japan, this is quite popular. I visit the Tokyo Institute of Technology, the lab of Professor Kazuhiko Kasai, this person, and he showed us the tall building in his campus that put on the base isolation. Okay, normally we would think base isolation we apply only to low-rise or mid-rise, but in Japan they seriously apply it to the tall building. Many tall buildings are placed underneath, put the base isolator under the building. So this Professor Kasai brought us down to see the base isolation underneath the building. Okay, you can see large rubber bearing. So in order to understand how isolator suppress the response, you need to first understand how the tall building respond to earthquake ground motion. Okay, so I prepared some animation. This is a tall building with a fixed base, not isolated base. And this is a response in the first mode. The structure has many vibration modes. This is a response when the structure sway in the first mode. You can see this picture shows the lateral displacement. It's large displacement at the top, zero displacement at the base. On the next picture shows the shear force. The middle graph shows the shear force. And on the right show the overturning moment. Actually, all the response in this mode, they are all proportional. Actually, proportional to displacement. Proportional to what we call modal coordinate. Okay, that's a response in the first mode. This is a response in the second mode. The structure will deform in a different shape, more complex. The shear force also quite complicated. And this is overturning moment for the second mode. They all also they vary with the time, but they are all proportional to modal coordinate. This is a third mode. Okay, similar, but the pattern is different. Third mode is different from second mode. Second mode is different from the first mode. In reality, when earthquake shake this building, it will be a combination of all this. You have first mode combined with second mode, combined with the third mode, and maybe fourth and fifth and higher modes. So you can see the complex lateral sway. You can see the complex response pattern of the shear, complex response pattern of the moment. But you can see this dashed line shown on both sides is a kind of upper or maximum, upper bound, lower bound, positive bound, negative bound. We call this the demand. Shear demand, moment demand. Okay. So we can actually estimate the response, maximum response by showing the dotted line or the dashed line, showing the maximum shear and moment developed in the structure. This is a work of base isolation of tall buildings. We are actually trying to study because building in many countries in Asia, they are quite different from buildings in Japan. In Japan, they apply moment frame system. But in many countries here, we have shear wall, shear core, plus frame. So Anastasia and Nimala, these are two students working at the 2 different years. One is coming from Indonesia, the other one from Nepal. Both are coming from earthquake active country. They are interested in this topic and they work on this topic. They are master students. So we study if what will happen if we put the tall building under base isolation system. So you can see here, we have the plot of many response. This the one on the left is a story shear. The red color is the fixed base case. The green color is base isolated case. You can see the great reduction of shear force in the building by this simple base isolator. The next one, that one in the middle, show the story drift ratio. The damage to the panel, to the wall, depends on this story drift ratio. Okay, and you can see a great reduction of from the fixed base case to isolated case. The one on the right is a peak floor acceleration. This is an indicator of the impact of earthquake on the building content inside, the furniture, computer, any content inside the building. The damage will depend on peak floor acceleration. So we can greatly suppress from fixed base to isolated case. So this kind of a base isolation technique, or we call technology, can actually help you design the new generation of the structure that will be much safer and can be serviceable right after the major earthquake. Okay, now I come to the last topic that I want to highlight in the research. It's about rapid identification of seismic damage by using acceleration response time history. Well, this picture show the building with red dots. Red dots show the location where we put acceleration sensor, or we call accelerometers. Accelerometer looks like this in this picture. It's a very compact vibration sensor, measure floor acceleration, horizontal components, vertical component. Okay, the cost is not high. We can put it in many buildings. We put it at some location on the top and the mid part, at the base. Okay. The question is, how can we make use of this acceleration data? The sensor itself measures acceleration response, but in order to estimate the damage, we need to know not only acceleration response, but many other response. Okay. The traditional approach by using acceleration sensor is to use this acceleration data to calculate natural frequency, mode shape, and damping ratio of many vibration modes. Okay. When the structure is in initial intact condition, it will have a certain value of natural frequency, damping, and mode shape. But after the seismic event, there will be some change in natural frequency, some increase in the damping, or some change in the mode shape. This can be used to identify the structural damage. This is a traditional approach, but we think that this approach is not effective because the change in natural frequency, change in mode shape, in general are so small that it's hard to identify the damage. So in our approach, we are not doing this way. We actually try a different approach. At AIT, we actually, from the acceleration sensor, we are trying to first extract modal acceleration in each mode. And by integrate them twice, double integration, we can get modal coordinate of each and every important modes. You know, all the response is proportional to modal coordinate. So we can estimate all the response, either story drift, flow acceleration, bending moment in the wall, shear force in the building. We can all compute it. We can compute this response mode by mode, and we can sum them up to get the total response. So that is our idea. This is the work by two more students, Mr. Chananwat in 2020, Mr. Navindra in 2021. So we actually put the acceleration sensor at only some floor, not the entire structure, just floor 34, 23, 11, and at the base. Based on this, we modify the measurement data a little bit, and we pass the measurement data through a so-called orthogonal filter. We can actually break or transform this response into modal acceleration. Mode 1, mode 2, mode 3. So from each of these, we can compute modal coordinate for each mode. And from each modal coordinate, we can compute story drift, shear force produced by that mode. And then when we combine all this, we can compute the response, any response we want. This is show example. There are many colors, but in this case, the building is subject to L central ground motion. And the black one is the real base shear. The black one shows the base shear and the moment. The black color is the actual response obtained from the detailed nonlinear finite element calculation. The red color is the estimate response from acceleration signal. In producing the red color, we only use the acceleration data, and we extract modal coordinate, and we estimate the shear and moment. And you can see that we can predict well both shear and moment. Okay, we can actually do the same for other response, and we can compare this response in the structure with the capacity of the structure. We can compare the demand with the capacity, so we can estimate the level of damage. This is a plot of the upper bound, lower bound, positive bound and negative bound for moment, bending moment or overturning moment. On the right hand side is a story drift along the height. You can compare the black one with the red one. Okay, so you can see that we can predict quite in a reasonable accuracy of the response of the entire structure. And by this way, we can quickly estimate the damage or the impact of the structure, impact of the earthquake to the structure. So actually, this is a numerical study, not the real building. So I assign the work of experiment to another student, Mr. Abhishek Rekmi. This is a model, physical model of about 2 meters high. We put in on our shaking table. That's how we design our experimental model. We put a lot of accelerometers, the red color dot on the top and the mid, 4 of them at the base. And in this experiment, we also put the strain gauge to check the bending strain, and put a diagonal strain gauge to check the shear strain. And they are located here in a mid height and near the base of the structure. And then we conduct checking table experiment to test the concept. Okay, we want to test that if we measure only acceleration, can we use that acceleration to estimate the bending moment and shear or not? Okay, we just use acceleration to calculate the bending and shear, but we also measure bending and shear directly just to compare the result to see whether we can predict it or not. So this is a test. We conduct many tests. This example of the test for small shaking. We simulate L central ground motion.
If we apply one factor, it will break AIT. It's like going.
Oh, this is a small shaking. L central was scaled down to 10%, and this is a large shaking. You can see this. Well, actually, we try to create damage to this structure, but structures remain elastic. So this is probably the last slide. Okay, you can see this one is bending strain at the base, shear strain at the base, bending strain at the mid height, shear strain at the mid height, and there are 2 color graphs. The red one is a direct measurement, and the black one is the estimate from acceleration data. So you can see that we can actually predict it well. Using only acceleration data, we can predict what will happen, how the shear response will vary with the time, how the bending moment will vary with the time. I think this goes the same for other response. So this is an example of research work that we are doing at AIT. We are trying to prepare for the future, testing many new ideas, new concepts. But actually there are many more that I cannot explain today because they're giving me a time limit. If I have no time limit, I can cover more. So I think that's all. I hope you enjoy this presentation. Thank you for your kind attention.
Thank you, Professor Penang. We will see again Professor Penang in the afternoons, parallel forum. So please watch out for that too. Now, please welcome Professor CVR Murthy, Professor at Indian Institute of Technology, Madras, Chennai, India. Professor Murthy works closely towards earthquake safety of built environment in India. He is engaged closely with the National Disaster Management Authority, Government of India, to prepare policy, guidelines, and implementation strategies. Currently, he is a member of its advisory committee. Also, he is the chairman of the Earthquake Engineering Committee of the Bureau of Indian Standards and steering a comprehensive upgrade of the earthquake design standards of India. He has authored and co-authored 6 books on earthquake-resistant design and construction. Professor Murthy will share his extensive knowledge on building competence and structural engineers of the future. Please go ahead, sir.
Yeah. Thank you, Jennifer.
Sorry. We can see now, sir. Thank you.
Yeah. So good morning, ladies and gentlemen.
The discussion that I will focus on will be about building competence in structural engineers of the future. Hearing all the colleagues this morning is very humbling to see what the future is going to be and what the demands are going to be. So what I'd like to place before all of us today is that it's a collective responsibility towards future-proofing the built environment, and we need the hands that can really build the future of this world. I'll spend today's attention on concepts, on tools, and traits. To begin with, I'll mention here that when we look at the built environment and the role of structural engineering, I would say there are 5 tenets that we need to follow, and that is safety, functionality, durability, aesthetics, and economy. Very clearly, the top 3 are non-negotiable and in that order, and the only negotiation that can happen is with aesthetics and economy. If you pay more, you get better aesthetics, otherwise you will get much simpler structures. And this is where the game of structural engineers is that how do you really do this balancing act? And that's where I place that there is an art in this entire balancing act. And that is what we will look for in the coming minutes. When I talk about competence, 3 aspects come into focus. One is positive attitude, second is skills, and third is knowledge. And very clearly, it is positive attitude that's the starting point. And only then, if you have that positive attitude, can you really build skills and knowledge. If you do not have that positive attitude, any amount of skill and knowledge you have will actually be not using that for the good of the world, good of the built environment, good of the people. And that has been the focus of the discussion since morning when Mr. Ashraf Habibullah started the discussion. Attitude is a way of thinking or feeling about someone or something. It has to do with the heart. Skill is an ability and capacity to undertake systematic and sustained effort, and this has to do with the hands. And knowledge is the human capability to interpret available information, and this has to do with the head. It's the 3 together that actually make us a complete person to be able to serve the humanity at large. Coming into the center space of structural engineering, there are 7 virtues that the built environment needs to be endowed with. And these are, to begin with, a good configuration, initial lateral stiffness, at least a guaranteed amount, at least a lateral strength, some ductility, and assured deformability, desired collapse mechanism, a preconceived desired collapse mechanism, and ultimately the energy absorbed by the structure. All of these have to come into the process of structural engineers' effort to do the computations to ensure that the built environment is safe against the various loads that are placed on the structure. And it is these 7 items that actually have led to the progression of the design methods. Today, we can place all the design methods on 4 steps: the stiffness-based, strength-based, deformation-based, and energy-based. This stiffness-based has been discontinued for some time now because it has not resulted in successful designs. Currently, we are practicing the strength-based design, but very shortly, I suspect that we will have to bring in the deformation-based design into the codes of practice, especially the importance of having a predetermined collapse mechanism and assuring a certain deformability in the structures. Also, in the road ahead, it is possible that we will look at the energy absorption capacity of the structure and decide whether it's going to be elastically contained and through the help of isolators, or inelastically absorbed through damage induced in the structural members. When you look at today's design practice, we know our material, we design a section, we detail a member, and go ahead and construct the structure, right? But in the current design process, we don't assess the structure, at least analytically, and do not understand what is the collapse mechanism that we are offering to the people at large. In effect, we are doing the forward loop in the design practice and not the backward loop. I suspect that in time ahead, when the people of the world will ask us for safety as structural engineers, we are bound to do the closed loop design and not just the open loop design that we are offering today to the people. To do all this, the structural engineer should have strong concepts, and in particular, these strong concepts will reflect through the hand calculation one does in trying to assure that the numbers coming out of the computer calculations are actually reasonable and well placed. The second most characteristic that the structural engineer must possess, the virtue that one must possess, is physical intuition. You should be able to feel the deformed geometry of the structure and thereby understand the physics behind the mathematics, and not just the mathematics of the physics that we are focusing today on. In the road ahead, this is going to be a determining factor on the quality of structural engineering that we will do, whether we are really understanding the behavior or we are blindly doing the numbers. Another crucial feature is the structural engineer must feel how the forces are flowing through the structure and clearly understand that every time the load paths bend, that there is crisis, and providing structures with the least number of bends in the load path will be the focus in the effort in structural engineering in time ahead. Another important feature that one must be, a structural engineer must practice in the time ahead is actually sleep with the mode shapes and natural frequencies before you start doing any calculation on the structural design. The reason is that the missing masses, the extra stiffnesses that we have offered in certain locations, or the excessive flexibility that we have in a few elements in the structure, all these have to be weeded out before actually you go into the design effort. And that is why understanding the dynamic characteristics of the structure is going to become the starting point for doing an improved quality of structural design in any type of structure, be it a building or a bridge or a water tank or a retaining wall and so on. In all structures, one must know the natural mode shapes to be able to say whether you have proportioned the structure reasonably. Also, it is important that the most of the entire response is taken away by the early modes rather than the higher modes. In particular, torsional mode has to be kept away from being a center space of the structural response. Clearly, there has been an interest in quantifying damage over the years, but a clean understanding of it has not yet been placed in terms of quantifying damage. And this is the time where the next 2 decades, we will have to quantify damage, because when we talk about resilience, when we talk about risk-based design, the cost loss and the loss of life and so on, we need to quantify the damage in the structure. And only then will we successfully propose a design that is acceptable to the society. So here is where we are looking for a novel way of looking at the quantification of damage. Another thing that is essential in a structural engineer's career is not to just get stuck on one item, but to actually complete the full end-to-end of that subject that one is picking. For example, if I take the story of dams, one must know field tests, one must do some analytical work, and one must do some laboratory work. And in particular, each of these has more nuances. And let's take the analytical work alone. And you look at it that you will do equivalent static, you will do response spectrum method, pseudo dynamic method, and the dynamic method of analysis. And likewise, I can show pictures for field tests as well as for laboratory tests. This is where it is time for structural engineers to take a particular system, a particular structure, and develop holistic competence in that one area, so that the world will gain by the knowledge, skill, and attitude developed by this colleague for the good of the society. One important point that has slowly been neglected is actually the use of tested technologies. today the industry is running faster than the R&D, and as a consequence, many untested technologies are being pushed into the market, and they are practiced even without the availability of standards, especially in countries where there is no techno-legal regime. Excessive use of precast buildings in seismic areas without any experimental backing, and pre-engineered buildings and so on has become a menace in many of our countries. This is where full-scale testing of structures will be essential, especially when we are adopting type designs and repeating them in tens of thousands units built across the seismic regions. So it is necessary for the nations to build full-scale testing facilities to be able to say guaranteed that these schemes of housing that we are proposing for the people at large are indeed safe, and that people can live in them and be assured that they are not going to collapse. So tested technologies alone should find center space in the future of structural engineering. On the same breath, I would like to say that poor structural systems should be weeded out. We should not permit technologies that have shown poor performance in the past, especially unreinforced masonry in seismic areas, open ground story buildings, and flat slab buildings. These have been practiced without even understanding the implications of their behavior in strong earthquake shaking. What we see today is that if we are very modest, we will grow to be about 40% more by the 3 decades, 2050. But if we are a little more excited, we will be 60% more in population. And if we are much more engaged, we will become 100%. We are doubling ourselves in the next 30 years. What this means is that there's going to be a huge urbanization that is going to happen. And unfortunately, we are going to densify most of the urban areas. And this is not something that we are going to do it so easily if our structural engineers are going to be not having the necessary background and competence to be able to build such structures which offer larger densities for the governments. As of now, we have a large stock of buildings across the world which have been built, but we don't feel that all of them are necessarily safe. So the 2 promises that we have to make is that all new structures will definitely make them safe. And so the standards have to be raised for that. Alongside, the second promise we have to make is all the existing structures that are unsafe, we will have to do a retrofitting of the same, right? Clearly, retrofit is a very tedious, long and arduous task. We can't retrofit all the structures, but definitely we need to actually quickly, urgently consider giving priority to critical structures, lifeline structures, schools, office buildings, and select residential buildings also. Here is where the different structures will require different solutions, and that is where structural engineers have to start raking their brains to bring out possible retrofit solutions for the different structural forms, structural systems that are adopted in different countries across the world. Here is where to be able to retrofit, one needs to have a 4-level assessment method so that we will be able to shortlist the structures on priority and do the retrofit in them. So two levels will be for qualitative filtering, and 2 levels will be for quantitative. We need to get started with the simplified quantitative to be able to make a difference, because we don't have too much time at this point of time. When we look at the levels of effort that we need to put in the assessment, either risk assessment or vulnerability assessment, we notice that as we go higher to the 4th level, will require a lot more time and rigor, and which we cannot afford. But fortunately, if you have a telescopic method, we will be able to bring down the scale of structures, the number of structures by orders of magnitude at each of these levels. And hence, we need to quickly have in place all the 4 levels of filters so that we can effectively make a difference in the retrofit, and not just blindly embark on retrofit without having any understanding of the relative positioning of the various structures in a community. While I'm speaking, there's a large number of vendors who are actually providing repair services and they are, in some sense, coercing the users to think that this repair is retrofit. And this is where I want to halt for a moment and say repair is not retrofit. One needs to be very clear that 2 millimeters of a wrap on a column is not going to change the overall stiffness of the building. And that is where the holistic approach from global to local, first fixing global parameters like overall lateral stiffness, overall lateral strength, and then deformability and ductility. Those have to be contained first before one really gets into understanding what individual members can contribute. So whole to part is the strategy that we need to adopt in the retrofit approach. One interesting feature that is going to draw a lot of our attention in time ahead is the fact that in the 1970s, the cost of non-structural elements was only about 5% of the project cost without considering the land cost. But today, non-structural elements are climbing and they are at 60% to 90% of the whole project cost, depending on which structure you're building. If you're building a residential structure, your finishes are 60%. And if you're building a hospital structure, they can go up to 90%. So a lot more attention needs to be given to non-structural elements. Structural engineers have to understand that the non-structural elements need to be secured and through formal processes to be able to guide the architects with simpler strategies that they can provide as details when they give the finishings of the structure. An important area that will grow, especially when we are talking about retrofit, is actually nonlinear analysis. Today, nonlinear analysis is not part of the undergraduate education, and also in the master's education, it is only in select institutes or universities worldwide that they teach nonlinear analysis. If the world has to be retrofitted, and if the current built environment has to be secured back to safety, we need more structural engineers to understand comfort and be comfortable with nonlinear analysis, which of course has two parts, the geometric nonlinearity and the material nonlinearity. And we pray that this becomes part of the mandatory curriculum in time ahead in most countries, at least at the master's level, though not at the undergraduate level. When I talk about nonlinear analysis, so far I was talking about knowledge issues, but now I'll talk about skill issues. When you talk about nonlinear analysis, the computational speeds have improved significantly, but we can do better if we can come up with FPGA programming to have various nonlinear elements, not as an element library in a software, but as a chip library in the hardware. And so we should be able to come up with chips which can do specific nonlinear truss analysis, nonlinear frame analysis, or detailed finite element analysis of a deep beam and so on. All of these can go into the hardware side, and that is where structural engineers have to engage with electrical engineers and computer scientists to be able to do this work and bring faster gains and more steady performance of the nonlinear systems, especially when you're looking at graphic user interfaces and you want it in real-time condition. You may want to go, you may be required to go into the FPGA program. While I talk about programming, while structural engineering software will continue to support today's needs, I think with the growing time, the structural engineers have to become more sensitive that they need to verify all their numbers through hand calculations before they sign on a drawing good for construction. And this is what we are hoping that we can inculcate hand calculations in the future structural engineers alongside the use of structural engineering software. And this is where when we talk about hand calculations, that is one part of it. But there's another part of it that structural engineering graduates should be able to actually become the future software writers. And for that reason, I would believe that some of them have to really think about getting into writing computer programming, learning computer programming languages, and at least have a skill or a capacity to have drawn a 6,000 line nonlinear analysis computer program, so that they should be able to understand the nuances before they become the future software developers. Design offices will continue to need computational tools, and so MATLAB, Excel spreadsheets will also continue to be in the center space for many of the design offices. We talked about big data this morning. The skills required for big data are actually going to be quite different from what normal structuring classrooms teach you. You will need to understand probability, you will need to understand statistics, and also the classical mathematics of either linear algebra or even differential and integral calculus that will come into space. This is again an interface area where we as structural engineers, we have to work with the electrical and computer science engineers to be able to create meaningful outcomes of the data that we are recording in large volumes in time ahead from different standpoints. BIM is going to become a central focus in most construction activities, and structural engineers do require to understand BIM to remove all conflicts before at the field they come back to you saying that this drawing is not acceptable. And so well before we get into construction, all the conflict resolution has to happen, and BIM in structural engineering is now a very formal subject, and that is going to become like a fundamental tool for the structural engineers in the road ahead. We talked about structural health monitoring. We also need to do load testing of some of the structures. We need to continue to capture ambient vibration and force vibration responses, and especially when there is severe shaking, we will also collect inelastic responses from the structure. So this is where sensors and instrumentation. So as a structural engineer, one needs to have a good background of signal processing. One needs to have a good background of interfacing various devices, especially the use of drones and so on, that has increasingly becoming common in structural engineering practice, especially post-earthquake damage assessment or even monitoring the structures, their structural health. So structural behavior, load assessment, dynamic characteristics, they will be the center space of all the testing that we are looking at in the future laboratories. I'll go to the third aspect, which is attitude. And when you look at different structure types, you'll definitely require higher and higher rigor as you go to the more critical and special structures. And also the performance expectation is very high on the structures. This is when I would say that one needs to accept the rigor that is required for the different structures and be abreast with all the competence to be able to provide a successful design or maintain an existing facility. So in structural engineering or in civil engineering, when we start doing our work, we realize that we make 3 mistakes. And these 3 mistakes are error of intention, error of concept, and error of execution. Now, for all of these, error of intention is the most dangerous, and this is not acceptable in professional practice. And we are looking at a techno-legal regime to be definitely in place in many countries which don't have techno-legal regime as of now. This can alone reduce the error of intention. And you look at error of execution, we need licensing of engineers, and the error of concept has to come through capacity development. So one of the key aspects of future structural engineers is they have to accept that the learning process is not halted after graduation, but it will continue throughout the lifetime. That is the first thing. Second thing they have to accept is that they have to write this licensing of engineers examination periodically to be able to maintain their status as those empowered to be able to design structures for the world. And finally, all structural engineers have to accept with humility that they will be following a techno-legal regime. And the intent is not to necessarily comply with the standards, but also provide safe structures for the world to live in and conduct themselves. So in here, very clearly, in many countries, we don't have structural safety audit. And so we have to begin that urgently. If you really want to make this world a safer place, we need to move from a no audit regime to a 100% audit regime. And the structural safety audit is definitely one of the items that has to be on the table. Another practice that's not there in many countries is the issue of quality control and quality assurance. And we need to bring this third-party independent peer review system in place so that the building owner has the confidence that indeed the facility one is considering to build or develop is in keeping with the best principles of safety for the people of that community. Licensing of engineers will be center space in time ahead because we are looking at mobility of engineers from one country to another. This mobility will be a key factor where we should be able to go from one country to another, because today projects are run globally and you have to design projects for another country's standards. And hence we need a strong base of teachers who understand standards of other countries, and we need a strong base of structural engineers. And this can happen only if we have a level playing field, which is achieved through the licensing of engineers process. In effect, what we are looking at is a structural engineer must have the capacity, not only just for planning, but also in detail on analysis, understanding behavior of structures, being able to design structures by different standards, understand the nuances of construction, though not stand there and do the construction themselves, and then have the clarity of what are the issues for maintenance, what are the items to keep an eye on, and then eventually retrofit, provide retrofit solutions for some of them. And an individual should have this 360-degree education. And this is what we're looking at. End-to-end competence will also mean at an individual level, one has to look at all aspects of that particular structure, but within that, there are these 6 features that have to be taken care of by every individual. A structural engineer is not complete unless the person has put hands on all of these 6 aspects in their career. What I'm seeking as a consequence of all that I have said so far is that the component education that is a practice today alone will not suffice, and that we need to go to system level education. And so curricula across the world in various universities have to change, and life has to be made a little more simpler than what it is today. Clearly, there is no place for complacence, and competence development has to happen in a proactive way, especially the development of positive attitude will be the focus of the road ahead. I'll make my closing thoughts come through here. New structural engineers will have to focus on 5 aspects. That's education, research, technology, safety, and implementation. And there are a number of aspects that some of them I have already mentioned now that they have to undertake so that they will be able to provide the services needed by the community. What we notice is out of all these aspects, there is a share of the industry that is related to technology and safety. They need to provide the retrofit skills to be able to retrofit structures. They need to conduct structural health monitoring. Standards of practice have to be improved. Manuals of good construction practices, good design practices have to be brought in. Full-scale testing is something that they will have to undertake if they are proposing newer designs. I talked about FPGA programming and the new pedagogy. They need to suggest what is required for them. Also, government has to spend a lot more attention on ensuring techno-legal regime, promoting pilot projects, watching the type designs and making sure that they are safe, undertaking risk assessment and sharing with the people the level of risk that we are at. And then continuing education should be regulated so that all the practicing engineers will be able to take that in the true spirit. And on the other hand, the academia has a very stiff role because they will have to feed all the mouths that are there by changing the curriculum, especially bringing nonlinear analysis and the new design methods into the use. And if we can do all of these together and collectively the academia, industry, government combined can do all these items together, we will definitely make competent structural engineers in the road ahead. Well, I may have spent a lot of my attention either on the college going students or on those engineers who are employed, but I must confess that follies at the in parenting and in the childhood and school days cannot be corrected at higher education or in employment. So in effect, what I'm seeking is that competence development is a lifetime process. And for those who are young and who are middle-aged, it is time to make better parenting happen so that the future structural engineers will come out with positive attitude and that they will be able to build this nation or this world with better and safer facilities for all of us. We are at a certain point of time when we begin our lives and we want to go somewhere. That's our target. And many a time I see that there's a urgency or a race to do some shortcuts. Well, that may not be the path. Often the shortcuts don't lead us anywhere. And this is where we have to understand that we need to look at a long range perspective. We need to have a long range perspective from childhood to school to college to employment to retirement. And only then you will be able to calmly provide the needed services for the good of the people. And I can very clearly say that a structural engineer has to keep crusading with the 5 elements of nature all the time. To do that, one needs to have a big picture clear as to what the new project is going to be fitting in the context of the existing built environment. What will be the geometry of this structure? Will it come in the way? Will it impose itself? Will it disturb the aesthetics of that particular environment? Or do we have enough land for undertaking this? Structural engineer must continue to imagine the new and the innovative forms which are actually going to be more functional and also appealing to the eye rather than the relatively straight-jacketed boxes. On the other hand, we have to push the envelopes of our analytical capabilities and go towards the forensics. We need to be able to preempt what will happen to our structure in the time ahead if a certain load form has gone past its number, and if we get really realized loads which are larger than what we get, will the structure survive? If not, what will be the situation for us? Can we correct it by doing some detailed nonlinear analysis at the beginning itself without waiting for the eventuality? Structural engineers should have the design acumen to be able to provide that imposing structure that every owner wants to have, that special unique structure that every owner wants to own and have the name across. Structural engineers must provide designs and solutions that can be executed and also go and watch that execution happen, because then the next design will be that much more real in their own effort in the time. But all that said and done, 80% of structural engineering is actually common sense, and the remaining 20% is calculations. If with common sense you can get the whole framework in position, the calculations part will only be convincing and reinforcing your own conviction. But this is where I think we need to make sure that the new generation builds this common sense. Common sense cannot be taught. It has to be inculcated. It has to be focused through daily discussion and activity and examples of the past and the mistakes of the past. Ultimately, I will say that safety should be the driving seat. Safety should be in the driving seat for all of us to be able to say clearly that as structural engineers, we have made the world safer. I'll stop here by saying structural engineering is actually art in engineering, because it's not just left brain activity. There is so much about the right brain that we have to do, which is actually going to take us into becoming closer to architecture profession, closer to the society, and closer to the governance people, because we are supposed to accommodate all their qualitative questions into quantitative answers. And that is where we need the right brain becoming more active. And I pray that the future structural engineers will be able to do that better than what the current structural engineers are able to offer. And if your dream is actually to have a structural safety ensured of the built environment of the world, then it's time to get into action. Being a spectator is no fun in structural engineering. I think this getting into the play area, play arena is what the game is all about. The conditions are tough and they'll get tougher with time. But very clearly, there is a clear route that we can take of persistent hard work. And I'm confident that we'll be able to come out of this, because from untruth to truth, and from darkness to light, and from life to eternity has been the path that has been told to us over time. And so we will follow that and make this happen for the people of the world in the days ahead. I'll stop here by thanking Professor Naveed Anwar for this warm invitation, and also Dr. Ong for helping me in making this presentation happen. Ladies and gentlemen, thank you for your time and attention.
Thank you very much, Professor Murthy, sir.
You're welcome.
I believe the best person to summarize the morning session would be Dr. Naveed. So may I please call Dr. Naveed again to give us a digest as well as a quick rundown on what's going to happen in the afternoon session.
Yes, thank you so much, Jennifer. And what an amazing session this has been. I really, enjoyed a lot. And let me start with Professor Murthy and then go backward, because I think Professor Murthy, rightly, we asked him to be the last speaker because he has very clearly put things in perspective in a human scale, on a cultural scale, on a civilization scale, and on the things that really matter in the end. And especially he talked about the childhood to retirement. And I think myself and Professor Murthy, we are both in that end and probably going to understand the true world that he said. So let me just say that I really inspired by many things that Professor Murthy has mentioned, and all engineers, in my opinion, have to think beyond the tasks that they daily do. And I think that's the whole purpose of his talk, is to make us realize the things bigger than us, they are broader than our daily work. And if we don't keep that in perspective, then we might just get into the rut of doing daily things, not realizing the impact of those. And if you realize the impact of what we are doing, we might be then encouraged to do something different or more, because we know the impact in the end. But if we just think that I'm just designing the reinforcement in a beam, we can't think what the impact of that is. Actually, that has an impact. And we have to think all the way through what you are doing today. I mean, most of the people do not realize that one bar they're putting here is going to be constructed. Somebody's going to put it there. The wrong location will cause a damage or a failure or a shear and things like that. So every decision has a consequence. And if we believe that what we're doing is important, it's significant, then every decision we make will be clearly thought out based on what he has described very well. Then Professor Penning has actually given us a very good idea of what the research and application can do. And his presentation was really showing the practical aspects of the research application and making sure that the research and the applications are tied together. And we always try to find something better, that this is the new system, new way of doing things which may have already been done. So I think he gave some really good examples of what the true researchers are doing and how they're being applied in the field. This is happening in every university, not only in AIT. He just gave you one sort of an image, but I'm sure many institutions are doing similar way. You are doing similar way in your own right. So this is just to give you a snapshot of what academic institutions' role is, what researchers' role is in developing new things that we will be maybe used. Then I don't think I need to comment on my presentation, but it was more related to the keeping us abreast of the development, making sure that whatever is happening around us, we also embrace that, bring technology into things, because technology is one part of the solution, not the entire solution. It's just one aspect of what we do, but it needs to be also improved as we go along, because those are the tools of the trade. So that we have to sort of learn them and develop them. And like Professor Murthy said, that the engineers have to be programmers. Actually, I can share with you that most of these structural engineering software companies that I know and work with, 90% of the programmers are structural engineers. So structural engineers are actually the one developing the software for structural engineers. So that is something that, and then there's a shortage of people who do that. When 20 years or 15 years ago, when I used to ask in the class, how many people want to do a thesis on programming? Almost everybody would raise a hand. Now, almost nobody raises a hand, which I think has become so used to using the tools, they forget that they also have to be the developers themselves. So we encourage them to go into that direction. And then the talk by Ron Klemensik. It was just amazing because he really showed us how research in the labs, how simulation, how testing, how systematic development can lead to big breakthroughs in industry, which can completely change the way things will be done in future. And I think what he presented was really a seminal shift from how we construct all buildings, just like there were so many other things behind. So I think to me that is a really, a major thing that we witnessed. And in future, we will be, seeing the impact of that in the construction of all buildings. And of course, the starting talk by Ashraf sets the stage perfectly. He made us realize how important we are to the world and how important the world should be to us, so that we can design for the future generations and have that empathy and have that connection to the work that we do. And everything else is part of that. So I think this has been a great session. And we intentionally did not go into too much detail of presenting one, research paper of that, because I think there's a lot of conferences do that. Our vision is to give the broader view, the big picture, and encourage engineers to think beyond what they do daily. So I hope we were able to achieve that a little bit. Please join us in the afternoon, because that is the discussion session. Morning was presentations by a few of us. Afternoon is your session. Basically, you will be in charge. You will be talking and we'll be listening, and we'll be trying to engage and answer some of the questions that you might have. We didn't have a question and answer session now intentionally, because we want you to join the forum in the afternoon. And they will be divided into 3 parts. Jennifer will explain all of that, but please participate in that, ask questions, be part of the discussion. Some questions could be related to this talk, something else that you want to know or you want to share. So we will give you a chance at that time. So thank you so much for everyone joining. I was watching, we had about 300 people joining this session in the morning. So it's quite a good number. I know that different people are in different time zones and also have doing their regular work. So thank you so much, everyone. Jennifer, back to you.
Very well said, Ms. Dr. Naveed. So there you have it, ladies and gentlemen. Thank you again for joining us today. Our Tech Talk is not yet over, as Dr. Naveed mentioned. We still have 3 parallel sessions in the afternoon. So we have performance-based seismic design under Dr. Naveed Anwar, wind tunnel testing under Professor Penang, and structural assessment of existing buildings by Dr. Chaitanya Krishna. It's easy to join. Just click the breakout session below, and you can choose which room you want to join and just click join.